Okay, so what I'm going to do is I'm going to work through problem number 35 on page 101. What I want you to see here is, first of all, we are very slowly expanding our set of skills. The skills started with be able to predict the distance a projectile will go if you know it's a horizontal launch, if you know the launch speed, and if you know the height above the ground. And then we expanded that just slightly to say, okay, now it's not a horizontal launch anymore. Now it's a launch at an angle. And so we're still predicting how far it goes though. And that was our second skill that we looked at. And now we're going to expand it even more. And what we're still not covering the gamut of all possible two-dimensional hang on, I have to load something here before I forget. We're still not covering the gamut of all possible two-dimensional kinematics problems, but we're expanding the scope so that we can start to think about them in a more generic way. And the way that we're expanding the scope is that we're still dealing with projectiles. We are still dealing with a known speed and a known angle. But now, we're gonna change some stuff. Now, for example, we're not gonna know how high the projectile launcher is above the ground. And you'll see that in just a second. We're also gonna change the launch itself. Guys, we're gonna change the launch itself so that instead of being launched at an upward angle, in this problem it's being launched at a downward angle. And when you start thinking about the projectile launcher preliminary lab, what we're going to be looking at are a bunch of additional things as well. Asking completely different questions. Questions like, how long will it take to travel a certain distance horizontally? Or at what point will it, what is the highest position it will have above the ground? Or what will its maximum vertical speed be right before it hits the ground? There's an unlimited number of questions that we can ask, given that we know the path of a projectile is completely predictable. And that's still within the realm of projectile motion. It's just expanding it to think about all possible scenarios. What are all the questions we could ask? What are all the things we could know? And how could we find answers to the questions based on those things that we could know? And then that's going to kind of take care of projectile motion. And we're going to move on in a couple weeks and start talking about forces. And when we start talking about forces, what you'll realize is there's another world of two-dimensional kinematics problems. And those are problems that don't involve free fall. They don't involve a known acceleration of 9.8 meters per second squared straight down. They involve different accelerations. Sometimes we know what they are, sometimes we don't know what they are. And that's gonna open up the rest of the possible two-dimensional kinematics problems for us to think about. So let's start with this. So this is problem, not all what I wanted to do. This is problem 35 on page 101. And in this problem, so the key that I want you all to see as we start expanding our scope of projectile motion problems is that the framework stays the same. We start by drawing a picture. Emily throws a soccer ball out of her dorm window to Allison. Here's Emily behind the wall. She throws a soccer ball out of her dorm window to Allison, who's waiting below to catch it. Here's Allison. And if Emily throws the ball at an angle of 30 degrees below the horizontal. So here's the horizontal, here's 30 degrees below the horizontal. This arrow represents the direction of the initial velocity of the ball. This isn't a vector, it's an arrow. I've drawn an arrow that is pointing at an angle of 30 degrees below horizontal, okay? That also happens to be the direction of the initial velocity. If we say that this arrow represents the initial velocity vector, then we can say that, that this vector would have a magnitude of 12 meters per second. That's the initial speed at which she throws the ball. And it has a direction of 30 degrees below the horizontal. Okay? This is an arrow, but this arrow represents an initial velocity. Velocity is a vector quantity. It has a direction and a magnitude. The magnitude of the initial velocity is 12 meters per second. The direction of the initial velocity is 30 degrees below the horizontal. All right? And then the question is, how far from the base of the dorm should Allison stand to catch the ball? So what we're looking for is this distance right here. And it says, assume the vertical distance between where Emily releases the ball and Allison catches it is 6 meters. So if Allison releases the ball right here, then the distance between where she releases it and where it's caught is 6 meters. Not 6 meters above the ground, but 6 meters between where she throws it and where it is caught. So the ball is going to follow a path that looks sort of like this. And notice that its initial path, it doesn't start off moving horizontally. It's thrown at an angle downward. So it's moving already down as it leaves Emily's hands, or whoever this is, Emily and Alex. Okay, so there's my drawing. The next step is to establish a frame of reference, okay? And so there's a whole bunch of things that we can do here. There is a way to establish a frame of reference so that we sort of minimize some calculations, but I'm not going to do that because a lot of times what's going to happen in a problem like this is you're going to say, well, here's my position 0, the ground, right below where the ball is launched. And to the right will be positive, up will be positive. Let's just say that. That makes perfect sense, right? That would be a very reasonable place to put position 0. As it turns out, it would probably make the most sense to put it either right here or where the ball starts. And we could solve it and it would work that way. It actually would be easier, but I want to show you what happens when we do it this way because I know that many of you are going to do something like this. All right, and then, so now we've got our picture, we've got our reference frame. The next step in the process, notice that I'm not thinking like, how do I get the answer? I'm just following the process. That is the key, follow the process every time. It always turns out the same. The next step, identify vector quantities that are not aligned with our coordinate reference frame and break them into components that are aligned. So what do we do there? Because this one is weird. It's, first of all, is it aligned with our reference frame? I mean, how do you know it's not aligned with our reference frame? How do we know that we need to do something with this? Any ideas on that? Like, could we just put this in to the like kinematic solver? Is 12 the horizontal or the vertical, or what? The x or the y? How do we know whether this is aligned with our reference axis or not? Any ideas? Yeah.
Does it say in the problem it's a horizontal velocity?
It says in the problem that it's thrown with a speed of 12 meters per second at an angle of 30 degrees below the horizontal. This is the speed, that's how quickly it's moving. This is its direction. Yeah?
I think we only know when it's aligned, when it's either at 0 or 90 degrees to the horizontal.
Yeah, and it's, so you're 95% of the way there. It needs to be either parallel or perpendicular to our axes. The axes themselves can sometimes be tilted, and we haven't dealt with that yet. If we're dealing with axes like this, where up is vertical, where the y-axis is vertical and the x-axis is horizontal, then any quantity that isn't either perfectly horizontal or perfectly vertical is not aligned. Another way to figure this out is to draw it. Draw our coordinate reference frame. Here's our coordinate reference frame right here. Horizontal and vertical. And then draw arrows that represent vector quantities. Here's a vector quantity. It's at a 30-degree angle below the horizontal. So visually it would look like this. And it has a magnitude of 12 meters per second. We can see this is not either perfectly vertical or perfectly horizontal. So this is not a quantity that we can put into either our x variables that deal with the x-axis or the y variables that deal with the y-axis, because this isn't either x or y. It's a combination of both. It has some part of it that's left and right and some part of it that's up and down. So how do we deal with that? We use the vector solver. In this case, if we look at the way this is drawn, this is going down and to the right. We haven't done this yet, but if you use the vector solver, we can tell it that it has a magnitude of 12, it has a horizontal angle of 30 degrees, and it's not up and to the right, it's down and to the right. And the vector solver will tell us that the x component is 10.4, roughly. The y component is -6. -6? Yeah, because it's in the downward direction, and that is our negative direction. So that means if we think about this visually, the rightward component of this vector quantity is 10.4 meters per second. The downward component is -6 meters per second. We're going to keep working with vectors. Some of you are like, yep, got it. Many of you are probably looking at this and thinking, okay, I see a triangle, and I sort of get that. This is work that's going to be ongoing through our work with projectile launchers, and we're really not going to hit this hard until we start talking about forces. So just be aware, there's some, you'll need to be able to do this stuff for like initial velocities, and that's it for now, pretty much. Like you'll have to look at an initial velocity vector quantity that's not aligned with either the x or the y axis, and then you're going to need to break it into two pieces. One piece that's aligned with the x-axis, one piece that's aligned with the y-axis, and that's as far as you're going to need to go, right? That's as far as you're going to need to go. So, where do we put these in our equations? Like these are numbers, and we got to put them in the equations, but where do they go? This vector quantity right here is the initial velocity. But is this the initial velocity in the x direction, or is it the initial velocity in the y direction? And the answer is this is neither. This is the overall initial velocity. It's not just to the right or just to the left. It's not just up or just down. It has its own direction. It's on an axis that isn't the x-axis or the y-axis. Generally what we do is we just call this the initial velocity. It's 12 meters per second, 30 degrees below horizontal. Velocity is a vector quantity, it needs direction, it needs magnitude. There's our magnitude, there's our direction. We don't put an x or a y here because this is the direction. If we put an x, then what we're saying is the direction is either to the right or to the left. If we put a y, then what we're saying is the direction is either up or down. How do we know if it's left versus right, if it's the x-axis? If it's positive, it's going to be to the right. If it's negative, it's going to be to the left. How do we know if it's to the left or the right with the y, or sorry, up or down with the y-axis? If it's positive, it's up. If it's negative, it's down. What if this were negative? Could we have a negative here? Does that make sense? Positive and negative indicates direction. We already have direction here. There's two ways that we can think about if there were a negative sign here, okay? One way is a way that doesn't make sense, which is that we're really giving two directions at once, okay? So for example, if I were to say, go 5 miles west, east, does that make any sense to you?
No.
Go 12 feet north, south. That makes no sense. That's what would happen if we put a negative sign here. We'd be saying the direction is negative and also 30 degrees below the horizontal. That doesn't make sense. Things only have one real direction. Look to your left, right. It doesn't work. We can't do that. The other way that we could think about this mathematically is that positive, when we have an angle like this, generally implies in the direction of the angle. Negative would be in the opposite direction. So negative 12 meters per second at an angle of 30 degrees below the horizontal would be in this direction. It would be up and to the left. That's how it would actually mathematically play out. Positive at a 30-degree angle below the horizontal is 30 degrees below the horizontal. Negative is in the opposite direction, up and to the left.
What would be the case for directions such as north, west, or southeast?
So there's a couple different ways that we could think about that. One is, those are approximations, right? Like, what is northwest? I mean, is it exactly halfway in between north and west? Usually not. The other is, if we're being exact, then we draw compass rose, right? Here's north, south, east, west. Northwest is this direction right here. If we were using the vector solver, I would say this is up and to the left. And I would say that this angle right here is 45 degrees. Typically, when we're using compass directions, though, we will use a bearing. We will use a number. We'll say somebody is moving at 271 degrees on the compass. And then you know which direction they're going. It sort of maps to this, right? 271 degrees on the compass is like this direction. What's that on this? That would be 180 degrees, roughly, right? 270 on a compass is 180 on a standard coordinate reference. And I didn't make this stuff up. I watched, oh my gosh. I saw the funniest thing this morning. It was a Saturday Night Live skit where it was George Washington and a bunch of revolutionary soldiers. Have you guys seen this one? And he's like, this will be a new nation. This will be a nation founded upon the ideals of liberty and freedom and democracy. And we're also gonna come up with our own units of measurements that make no sense whatsoever. And then he just like launches into this thing about how like 12 inches shall be a foot and 5,280 feet should be a mile. And basically like that's an example. Like why in the world did the math people decide that 0 degrees was to the right? When everybody knows that for thousands and thousands of years, 0 degrees was straight up. That just doesn't make any sense, but that's what people do. Anyway, that's an aside. We now have our initial velocity vector broken into components. What are these components? If the initial velocity vector is 12 meters per second at a 30-degree angle below the horizontal, then the horizontal part of that is the initial velocity in the x direction. And the vertical part of that is the initial velocity in the vertical direction. We found our initial velocities by taking the overall velocity, figuring out how much of it is to the right and how much of it is down. What's the next step? the next step is we identify variables and we just start plugging things in. What's our initial position? That's tricky. In the x direction, it's 0. Our final position is unknown. In the y dimension, though, we have a problem because we don't know how far that ball is up above the ground. We're not told that. All we know is it falls until Allison catches it, and it falls 6 meters, but we still don't know how far above the ground it is. There's easier ways to solve this, but let's do it the hard way. Let's say that the distance between where Allison catches it and the ground is h. What does that mean? That means that the initial height is 6 plus h. Whatever that is, 1 meter, 2.5 meters, we don't know. Her hands might be up here, she might catch it like 2 centimeters above the ground. We don't know. The final y position is whatever that distance above the ground is. Our initial x velocity, we figured that out, it's 10.4. Our final x velocity, I hope by now you realize that's going to be 10.4 as well. And the acceleration in the x direction is 0 because this is a free fall problem. We don't know how long it's moving. In the y dimension, our initial velocity is downward, which is our negative direction, so that's -6. Our final y velocity, it's not 0. We want it to be 0 because we know that Allison's going to catch it, probably, but it isn't 0. It's however fast it was going right before Allison catches it. And our acceleration in the y dimension is -9.8 meters per second squared. 9.8 meters per second squared because that's the free fall acceleration in the direction of the ground. Negative because I said that downward is our negative direction in the vertical dimension. So now what? Now we've got like 2 variables over here that we don't know what to do with. But it turns out that if we think about this problem the same way that we've thought about all the other ones, those will take care of themselves. So let's look at the left-hand side. If we were to think about all our kinematic equations, what you're going to realize is we've got nothing. We can't do anything over here. We can't find final position without time. We can't find time without finding how far it went. There isn't enough information here to get any variables. So let's move over here. What could we find over here? Well, it turns out we can find everything. We have 2 equations that we could use to get from here to either final y velocity or the amount of time. If you were solving this problem for the first time, you might just be like, well, I'll just try both. And if you were to use the equation to find the final y velocity, you'd get there, and then you'd realize that that doesn't help you. And then you'd say, okay, well, what about time? And you can find time. If you set this up using the first equation that I showed you in kinematics, you will have the final position in the y dimension is equal to the initial position in the y dimension plus the initial y velocity times the amount of time plus 1/2 times the acceleration times the amount of time squared. If you subtract h from both sides, you get -4.9 t squared minus 6t plus 6 equals 0. See how I did that? I just subtracted h from both sides. It turns out it doesn't matter how far above the ground it goes. What matters is the displacement. The displacement is -6. It started 6 meters above where it ended up. It fell 6 meters. That's all we really need to know. Okay? And then when you look at the equation, you'll realize, well, we can put all this stuff into the kinematic solver too, right? Like if we realize that we can think about h as being 0 or 1 or 2 or 3, and that means y minus y naught is always going to be the same. It's always going to be -6. then we can just put into the kinematic solver an initial position of an initial position of 6, a final position of 0, an initial velocity of -6, unknown final velocity, an acceleration of -9.8, and an amount of time that we don't know. We're going to find the amount of time that goes by, and we get 2 possible answers. One that would happen before she threw it, which doesn't make sense, and the other is 0.65 seconds. So t is 0.65 seconds. If that's the case, then t over here is going to be 0.65 seconds. And now, just like before, we could put this into the solver, but if you haven't figured this out yet, it ends up just being these 2 numbers multiplied by each other because the acceleration is 0. So if we put it into the solver, it's just going to tell us 0.65 times 10.4, or about 6.8 meters. And that's the answer, right? This distance right here is 6.8 meters. That's how far away Allison needs to stand. It's the horizontal displacement. So think about that for a second, because what we just found is not anything about hitting the ground. We found a point along the path of this projectile that's sort of arbitrary. We don't know exactly where it is above the ground. We know it's 6 meters down from where it started. If this thing kept moving, it would keep going down and keep going to the right, right? If we think about this in terms of the equations from this ball to the ground would travel farther in the x dimension. It would travel for a longer period of time. It would have a different final velocity in the y dimension right before it hit the ground. But we don't need all that. We're just looking to predict where it is horizontally when it's falling 6 meters vertically. It's a little bit of a different question than what we've done, but we solve it the same way. Yeah?
Instead of using h for like other persons,
Yeah.
you have moved the point of origin of the 0, 0.
Yeah.
You moved it to where I was.
Yep, exactly. So, and thank you for saying that. Yes, so take a look at this. Let's say that I would have said, okay, well, let's just make this 0, 0. Then what happens? Then our initial vertical position is 6. Our final vertical position is 0. Same thing. We put the same thing into the solver. Another way to solve this would be to say, let's start here. Let's call this 0, 0. Then what happens? Then our initial position is 0. Our final position is -6. Put any of those into the solver, you'll get the same answer. Either way, the displacement is 6 meters down. Either way, it takes just as long to fall. Oh, thank you. I appreciate that. So that's, a lot of you are like, where do I put 0, 0? Where do I put 0, 0? It turns out it doesn't matter where you put it. It's just, you gotta put it somewhere so that you can refer all your other positions to that point. As soon as you do that, then you can put some numbers in for your initial and final positions and solve the equations. The answers you get do not depend on where you put it. We get to put 0, 0 wherever it's easiest. I would have put it here. This is where I would have put it, because that is some known point. We know it starts there and it ends 6 meters below where it started. We could do that with the projectile launcher too. This is basically a projectile launcher that's been aimed down. Okay, that is all I've got for you.